for patients. Okay, so today we're glad to have Katherine Fraser here as a speaker of the semester's last seminar. She got a PhD in Harvard under supervision of Matt Reese. She is doing her first postdoc in Berkeley today, these days. And okay, today she will tell us about her prediction for the axion test and execute test.
Great. So thank you so much for having me. For any of you who don't know me, I'm Katie Fraser. As you just said, I am a Miller Fellow at Berkeley, and I'm going to be telling you about some work with Ben Safdie, as well as his student Josh Bonobo and postdoc Mario Rieg, who's in Europe, about what happens when you try to combine field theory unification with axions that come from extra dimensions. In particular, sometimes those axions can come from string theories. So my talk today is going to be divided into three parts. First, I'm going to give you some brief introduction, why axions and why stringy axions. Then I'm going to go through some examples. I'm going to start with some simple field theory examples that just come from 5D theories. And then I'm going to talk about a few string theory constructions, both analytic and then some numerical constructions as well in the type 2B Axiverse. And then finally, we're going to talk about trying to generalize this bound. So through these examples, we're going to put some restrictions about what axion masses are favored, and we're going to try to make some general arguments using partial wave unitarity, as well as comparing to existing bounds in the literature in the examples that we study. Okay, so first, introduction. So very base level for any students in the audience. So axions are periodic scalar fields, and they typically come from one of two places. They either come from the phase of a scalar after spontaneous symmetry breaking, so we have a scalar phi here, and this theta here would be the axion, or they can come from compactifying zero modes of higher dimensional gauge fields. So for example, if we have a 5D gauge field A, it can come from compactifying on some circle S1, but it can also come from compactifying on higher dimensional manifolds, as we'll talk about later. Now, the two kind of phenomenological motivations for axions, one is this well-known strong CP problem, which is why is the neutron EDM so small? So the neutron EDM is measured to be less than 10 to the minus 10. And the question is why is that? So this is a cartoon kind of picture of the neutron EDM from a talk from some TOSI lectures by Anson Hook. And so the yes.
I was just wondering, so I've seen this cartoon many times. I was wondering why people like it, because it's like not correct.
Yeah, I mean, it's a classical analog. It's obviously not the full quantum picture. I like the cartoon because if you're talking to a non-expert audience, the classical analog kind of helps them picture it. And it's a pretty picture. I don't have a great reason. Yeah. I think there aren't great illustrations of the actual quantum effect. But yes, it's just a cartoon. But so the axion solves the strong CP problem because at the minimum of its potential, this theta angle is the expectation value is relaxed down to 0. So the other reason that axions are interesting phenomenologically is that they can be dark matter. So oscillating axions redshift like dark matter in the early universe. This is the standard misalignment mechanism. So this is an illustration from a talk here where above the lambda QCD scale, we have an axion, and then once the universe starts to cool, it starts to oscillate in its potential and redshifts like dark matter. So phenomenologically, that's why people are interested in axions. Now, why extra dimensional axions in particular? So 4-dimensional axions in QCD axions that solve the strong CP problem have a quality problem. So the axion that I mentioned on the previous page gets its mass from non-perturbative effects, which means they're exponentially suppressed. And the problem with that is that, particularly from quantum gravity, but in general, we might expect that there are higher dimensional operators that are not exponentially suppressed that could contribute to these processes. And so we need some smart way to be able to suppress those operators. Now, there are some 4D solutions using like Z14 symmetries or these ugly mechanisms, but they're convoluted. Fair enough. They are hard to come up with.
Operators, I would call ugly.
They're hard to come up with, and aside from the Z14, I don't know any other effective field theory solutions that actually solve quality. Sure, we can chat after.
Field theory, variants, meson-like operators. There's a whole literature on it.
Fair enough. But in any case, you do have to come up with some mechanism to suppress these polynomial operators. Now, one of the advantages of extra dimensional axions is that in the extra dimensional case, higher dimensional gauge invariants or generalized symmetries, equivalently, forbid polynomial operators. And so this leaves only non-local effects, so other types of instanton effects, and these are naturally suppressed. Now, these aren't necessarily smaller than the QCD instantons, you've got to check that, but they are exponentially suppressed, and so it's easier to suppress them sufficiently to compete with the QCD case.
So, and you that e to the minus s instanton, and you compute
It depends exactly on the type of instanton potential. So depending on the exact effect, you can compute, depending on the non-perturbative effect, you can compute what it looks like.
but the action could be, if you don't know how to compute it, the action could be order 1 and then it's not suppressed. So it's coming from some stringy instanton. Is that what
It can come from a stringy instanton. There are other cases where it can come from, so usually we're working at weak coupling. So we're assuming in the theories that we care about that this S instanton is going to be greater than 1 in the weak coupling limit. There definitely could be cases where you're not working at weak coupling and you might worry that S instanton would be large. But those aren't the theories that we're going to talk about.
Yeah, but then isn't that, I mean, then you're not solving the problem, because if you don't know how to compute that effect for strong coupling, I mean.
Sorry, the usual like scaling with alpha, like in the cases that we understand the instanton effects with the usual scaling with alpha, we can compute it.
Yeah, but I'm saying that there could be strong coupling effect where the alphas of order 1, alpha strings of order 1, that exponential is gone. So how do you compute that?
Yes, so we work in a weakly coupled string theory limit. I don't doubt that there are other examples where you can't compute what's going on, and that you might not solve the quality problem. Our point is that there's a wide class of theories where you can in extra dimensional cases.
But I'm not sure that you know all the instantons, even for the weakly coupled case. So that's my point. Anyway, we can discuss.
Fair enough. Okay. So specifically in the case of the string Axiverse, we're going to be talking about 10-dimensional string theory compactified on a 6-dimensional internal manifold to get a 4D effective theory. So this is kind of just a cartoon of that. And here, like I mentioned on the first slide, the axions are going to come from higher dimensional gauge fields wrapping cycles. And that means that there can be many different axions if there are many cycles. And something that is kind of unique to these higher dimensional theories is that their physics is determined by geometry, things like volumes and intersection numbers, rather than something separate that separate parameters that you put in, like in a 4D field theory where the symmetry baking scale is separate.
These axions, though, aren't related to QCD, are they?
So one of these could potentially have the right parameters to be the QCD axion, but most of them are not QCD. So all of this interest in axions, both theoretical and phenomenological, has motivated many different experiments. So there's a large variety of experiments. Yes.
Any question from an outsider? Are all of the things you're calling axions pseudoscalars necessarily? Could they be? So, is it obvious that if I have something coming from, this kind of geometric thing, that's going to be a 4D pseudoscalar? And if so, does that matter?
I think the cases that we're interested in are pseudoscalars.
That should be the case.
So they just call compare. There must be a scalar.
Yeah, so you also have Saxi. So this is supersymmetric. Most of these compactifications, it's n equals 1 Susie.
Like dilaton in the axion.
Yeah, usually we expect that there would be some other contributions raising the mass of this axion, so the other component. And so
Protected by this engagement?
they don't end up being protected in the same way.
I don't think it's obvious, but okay, fine.
It's because if you start with n equals 2 Susie, for instance, then, sorry, if you start in a higher dimension, it's the A5 pairs up with a real scalar to form a complex scalar of the n=1 multiplet in lower dimensions.
So Susie is playing a major role in saying, in
Susie's-
answering my question.
Yeah, so Susie is combining the A5 with the scalar.
And Susie, the Susie breaking scale is, Susie's clearly broken, so the fact that it's broken is not disturbing its conclusion.
Right.
Yep.
Fine, I'll trust
But it's typical that the imaginary component is the one that's coming from higher default.
Thank you. So as I was saying, there are many current and proposed experiments searching for axions across a range of couplings. And it's interesting. So these experiments here, for example, ADMX, haloscope, are looking in the range where we expect kind of standard misalignment dark matter from spontaneous symmetry breaking. And it's interesting, there's a lot of other experiments probing other regions of parameter space. And it's interesting to ask, in what natural theories do we find axions that are appearing here? And these experiments really take a variety of forms, things like light shining through walls, looking for trying to convert axions and shine them through a wall and then convert them back, looking for solar axions with CAST, looking for astrophysical bounds for things like supernova axions. So there's a lot of different experiments. And that was one of the reasons we were interested in this, because it turns out that in extra dimensional theories, the region between kind of about 10 to the minus 11 and 10 to the minus 8 EV ends up being particularly interesting. So ADMX is kind of up here, near where we expect the post-inflationary QCD axion dark matter. Exactly the region where you expect that depends a little bit on axion strings and how much of dark matter you think that they formed. But that's kind of the general region where misalignment field theory axions live. And it turns out that in these extra dimensional theories, if you want those extra dimensional theories to be consistent with a field theory gut, then you get axions that live in this range here, which is quite a bit lower. So where does this come from? So I should say QCD axions that live in this range, which is quite a bit lower. So where does this come from? So the generic idea on this bound is that the limits are from requiring EFT validity up to the gut scale. So this is saying that the string scale as well as the KK scale should be at or above the gut scale, which we take to be 2 times 10 to the 16 GeV to get unification in SUSY. Now this also ends up constraining FA because all three of these things, FA, MS, and MKK, are determined by geometry. They're not constrained in exactly the same way, but they all depend on the volume. And so if you want these scales to be larger than M gut, then that's going to give you some limits on what you expect for the volume. And we'll see this both through some explicit examples as well as from partial wave unitarity. And then once we have FA for the QCD axion, we know the relation between the mass and FA was computed nicely in this QCD axion precisely paper. And so that tells you what mass range is favored. Now, also, it's been shown in some previous work, and we also see this, that the FA also scales with the number of axions in these Axiverse constructions. In particular, as the number of axions increases, FA decreases. And so this will also, a lower bound on FA will also give us an upper bound on the number of axions. Okay, so before I go into details, are there questions about the big picture?
So this is axions coming.
So the idea is that in these Axiverse constructions, you can show that there's a correlation between the size of FA and H11, or the number of axions. So as H11 increases, FA tends to decrease. And so what you find is that if H11 is too large, or the number of axions is too large, then FA doesn't satisfy this bound anymore. This is going to give us a lower bound on FA.
So this depends on the Calabi-Yau.
Yeah, exactly. Yeah, so we're going to sample a whole bunch of those compactifications, and what you generically find is that. Now, there could be, I should say that this bound is not ironclad. There are exceptions to this. This is assuming, one, that you want gut unification. If you don't want gut unification, then you can use things like localization to avoid proton decay from higher dimensional operators. Two, we sample parameter space in this Calabi-Yau, for these Calabi-Yaus, but sometimes there can be tuned regions of parameter space that analytically you're just never going to reach by sampling if they just have too small a measure. And so we don't necessarily think through all the different possible tuned corners of parameter space. It is possible that there is some very tuned region of parameter space that goes outside of this.
But for a given Calabi-Yau threefold, the Cauchy number or Betti number is really pre-primary. That's really pre-primary, so that you can actually slightly distort the.
Well, so the that corresponds to the number of cycles in the threefold. So for yes, so you once you have the threefold, you can compute the number of cycles, and then you know the number of axions. But there's lots of different there's lots of different threefolds that you can sample, and each of those has, many, some of them only have one, depending on H11, sometimes you might only have one known threefold, but in many cases, there are many different options for the compactification of what that can look like.
But in your analysis of using Calabi-Yau tools, you take that as a free parameter and you try to see.
Yeah, so we sample for all sorts of different H1s. So we take it as a free parameter and sample across that. And I'll show many plots as a function of that in this talk.
But you got your order 100, and these are all light scalars.
Relatively light, yes.
Well, EV and below, right? So,
yes, yeah.
do I have to worry that these things are going to be hanging around cosmologically?
No.
They were never produced, you're saying?
Well, they can decay into each other. And then you can also, they can be very weakly coupled to the standard model.
And this is not radiation, this is dark matter.
Yeah.
This is matter, this be able to matter, so.
No, the dominant energy density might be coming from the oscillations of
Yeah,
the
sure.
Kirkman, but they're still particles. There's
Depending on, you can also,
degrees of freedom.
coming from the dark radiation axion can come from the.
Yeah, so these are not thermal, so they're not necessarily thermally populated. So sometimes they are populated by exactly. I mean, it depends. There's a small Friesen contribution to dark matter from these, but they're never in equilibrium, and so you have to actually go through and look at the cosmology. They can interact with each other and decay.
Whatever.
Yeah, so most of these are Friesen, so you're not expecting that they were ever thermally.
So even that's the problem. It's not that, if any one of them contributes on the order of 1% of a neutrino, but you've got 100 of them.
Many of them, they have such tiny couplings though that they don't necessarily. So we actually have a follow-up paper, not in this paper, that we look at the cosmological effects, and you can, study their interaction, and you can study the way in which they that the axions decay into each other, and basically the contribution. Sometimes you do have to tune the theta angles in order to have. Sometimes there is tuning that's required in order to not overpopulate dark matter, but you don't run into an issue with radiation.
You also have scalars too.
Yeah, so the scalars you expect to be heavier though. So those aren't necessarily a problem. Those are separate. We neglect their effects because you expect them to just be much heavier. But yes, that is an interesting direction. But we think that there are cases that are cosmologically viable. Okay, so now let's start with some explicit examples, first in field theory. So this, the simplest example you can consider is a 5D orbifold gut. And the central intuition is, like I mentioned before, the axion mass is constrained in extra dimensional guts because the same geometry which sets Fa also affects the other scales in the problem. So at the simplest level, you can think of this as just dimensional analysis. If you're in 5D and you have one scale R, then MKK, MGUT, and FA should all depend on R. And so they can differ by factors, but kind of that's the general intuition there. Now, let's go into the details a little bit. So consider a theory on M4. It's an orbifold gut times S1 mod Z2. So we're going to have a bulk gauge field G gut that's going to be broken by orbifold boundary conditions. We're also going to have an additional gauge field AM. This is charged under an additional U1A, which has exponentially good quality. And because we have no light charged matter flowing around here, that's coupled to it. And here, A mu is projected out of the spectrum since it's odd under boundary conditions. And the axion is the integral over A5 since A5 is even under the boundary condition. So it's going to denote that by theta. So in this theory, the gluon couplings come from the standard place, which is the 5D Chern-Simons coupling. So these G tilde couplings. And when you dimensionally reduce this, you find a 4D gauge coupling of the standard form. Here, this K is just the quantized Chern-Simons level. Now, if we want to know the decay constant in this theory, we can read it off from the kinetic term. This is up to the number of domain walls, which in the theories we're considering is going to be 1, but you can get an order 1 number from there. I should also comment that, which I'll get a little bit more later, but in cases where there's mixing, you have to be careful about the relation between what you're reading off from the kinetic term, which is basically just the gluon coupling and the actual fundamental field range. If they're mixing, they're not necessarily the same thing. I have an earlier paper with Matt looking at more details of that, which I'll talk about a little bit more later. But in this case, since we have only one axion, we can just read off FA from the kinetic term. So the gauge kinetic term, once we dimensionally reduce, is just going to give us the scalar kinetic term. And we basically from that can just read off that FA is equal to the square root of 1 over pi r times G5 squared. Now we can rewrite this in terms of the 4D gauge coupling, A alpha. And MKK, which is just 1 over r. And we find that FA is given by this expression, MKK times the square root of 1 over A alpha 4 pi cubed. So now we impose that we want this theory to be valid up to the gut scale. That tells us that the KK scale has to be above the gut scale. Otherwise, you have these modes that come in and ruin precision unification below that. And we take alpha gut to be 1 over 25, which is what you need for precision unification. And that gives us FA is equal to 9 times 10 to the 15 GeV, or an axion mass of 7 times 10 to the minus 10 EV, which is well within the favored range. So in the simple, so this is to give you some intuition. In the simple field theory case, we do find something that's within this favored range. So if MKK is smaller than M gut, then you have a whole bunch of modes that show up at the KK scale, these winding modes that are not zero modes. And that ruins unification because you have to take that into account with running and all of these other things. And you get very rapid running, and then you no longer end up with unification. So there are cases, like obviously in many cases, there are tricks you can try to use to still get unification, but you don't end up with anything that looks like usual gut phenomenology if you try to do that.
Because SU5 doesn't unify.
So this is in supersymmetric cases.
That's what I mean. It's just minimal supersymmetric SU5 doesn't unify. So you anyway need to assume that there are some kind of corrections.
Sure. The KK corrections end up being the threshold corrections end up being very large, so that just dramatically ruins unification. Yeah. Okay. So very briefly, for some intuition, why is 4D different? So in 4 dimensions, there's generically nothing tying FA to the gut scale. It's just a separate scale of symmetry breaking. It's just the VEV of U and PQ breaking. So this can be far below M gut without ruining unification. There'll be some logarithmic running that you have to take into account here. But as you're saying, you have to have some corrections anyway. And so this doesn't qualitatively change the picture in 4D, whereas in 5D, you have this whole tower of resonances. And so the picture becomes very different. Okay. So are there any exceptions? It turns out, sort of. So if you're considering a orbifold gut, or you can just considering a higher dimensional theory, one of the natural questions to ask is what happens when you warp this space? So in the warped case, it turns out you actually can get larger axion masses. But what ends up happening is that MKK is similarly warped. It's also warped down. So you don't end up with precision unification. And you do have, you can potentially have higher dimensional operators generating proton decay still, so you need something else to suppress them like localization. But you can end up with, lower FA, but then you don't get precision unification. So how does this work? So now instead of flat space, we have an orbifold gut with the usual metric. So we warp here. By this factor k, so e to the minus 2ky, where y is between 0 and pi r. Again, we obtain FA from the kinetic term. Now we get this factor here from the metric. And When we dimensionally reduce, we end up with this expression on the right. And when we write this in terms of GS over MS, now this is still a field theory, but this is suggestive for the parameterization that we're going to use later. What you end up with is that, so you can almost think of this as a definition here. What you end up with is that FA is going to be proportional to 1 over GS times KMS over this exponential minus 1. And in the case where this KR is greater than or equal to about order 1, this exponential term in the denominator dominates over that 1, and this just looks like something that's warped down. So FA is this prefactor here, square root of K ms over GS times e to the minus K pi r. Here on the right, I've just rewritten this in terms of alpha gut and MKK, which is also warped down. So MKK goes as K times e to the minus K pi r, just from computing the mass scale that you expect the lightest excitation. And so from this, you can see that both FA and MKK are warped down by e to the minus K pi r. They're the same, so we expect them to be about the same order of magnitude, with FA a little bit greater than MKK from which you can see from the form of this expression. If this is greater than 1, and if this is kind of order 3 or larger, and alpha gut here is 125, this can kind of cancel out and give you that this FA is greater than or equal to about MKK. And since MKK is also warped down, as I mentioned, we need to give up on unification.
Sorry.
Yeah.
Why do you give up on unification in warp space?
So the reason is that MKK is warped down below the gut scale here. So that bound that I had on the previous case is from the previous page where I didn't want the KK modes to come in and ruin unification.
What is the KK? It's well known in warp space that it's logarithmic running.
But the fact that you have this tower of states.
Yeah, as I said, it's well known that it's logarithmic, not parallel.
You still end up with substantial corrections to unification even in that case. And the phenomenology ends up being very different than the standard gut phenomenology that is being searched for. And
I think that's incorrect, because what happens is that you get logarithmic running and you can still unify it and gut.
You have to worry about threshold corrections though, which can be a problem.
Okay, but you'll always have threshold corrections even for your actual dimension.
Yeah, but so in our case, the threshold corrections are above the gut scale. So that's not a problem at the gut scale.
But it doesn't matter. Even in the warp case, you'll just get log running. There's no power law, and you'll get unification anywhere you want near 10 to the 16.
I think the threshold corrections end up being a problem, but maybe we can chat about that after. Yeah, so in the case, so in this case, if you end up with KR of about 3, then you end up with this FA that is outside of this range. It's below the range that we cited, and that leads to a higher MA. Okay. Other questions before I move on?
Can I do a
Yes.
experiment? So suppose I'm doing a 4D axion theory and do a KSVC axion, I introduce
Sure.
hyperfermions. So I'm trying to check the compatibility with these two examples. Right, so when I have this KSVC axion in 4D, I basically introduce heavy fermions with particular material. That's essentially the FA with some color representations and coupling, right? So if I further define demanding those, I can add arbitrary species of those heavy fermions. I further demand their consequences to allow the gauge coupling to unify. There are such possibility I can arrange that may be very complex, right? That I have to take into account all the threshold correction plus the logarithmic running conventions. I could
That's
achieve
precisely what happens in the warp case.
Right.
Those corrections that come in, the SU5 universal, and so you still get the running, and you can understand all the threshold corrections. That's precisely the warp case.
That's right. And then I want to deconstruct the 4D, just say it, right? So I think I can still achieve a unification by doing that.
Yeah, exactly.
With a lot of tuning in some sense, and with some level of tuning of the threshold corrections I introduced where this heavy fermion stuff.
Yeah, I won't say that you can never tune your way out of this. I think we're trying to make statements about what's generically true, not necessarily. I mean, you can tune a lot of things. I won't make statements about.
Yeah, it's,
That's the one.
right. Depending on how precise you want them to unify, right? Which order you take into account. Of course, there's some precision calculation needed, but in principle, I can achieve unification. Which in your first example of the actual dimension without working, I think you're basically assuming those fermions are heavier than gas scale, and that you derive your result in my for each.
Yeah, you're assuming that the extra dimensional, yeah.
And in this second example, you were saying, I admit they exist, and I don't want to calculate what's their correction to my unification, but I assume their scale is still.
I mean, so we cite some of the older literature that does some of these calculations, and the claim there is that it's not that you don't end up with unification, but clearly we have a discussion to have after the fact because clearly there's a disagreement here. But yes, this is assumed. Yes, the claim is that there is no precision unification if MKK is worked down.
And you call it generic because I think the some keywords for you to have in these two examples generic, which you don't want to deal with the complexities of.
Yes, so yes, the claim is not that you can never find a configuration where you can precisely tune away from these situations. The claim is that in the ordinary scenario, if you just do the calculation, it doesn't come out automatically. Okay, so let's move on to some more complicated examples. So first, let's start with a 5-dimensional stringy analog. So rather than starting with 10D string theory, let's assume that all of the dimensions have already been compactified with size the string length. Now here, the standard model gauge group is going to be from fields localized on D branes, and the axion is going to be a 0 mode of a bulk 1-form gauge field C1. Here, you'll notice there's a slightly different normalization. That's just conventions used in the string theory literature. So this action is going to take this form here. So there's a Ricci scalar term, there's a gauge kinetic term, and then there is the axion kinetic term. This is going to give us the axion kinetic term, as well as this term from a D0 brane with world line wrapping S1. So again, we can dimensionally reduce this term and read off the axion decay constant, which gives us that FA is equal to the square root of MS over 2 pi squared R. Yeah.
When I write down the action here of the theory coming from the string theory, how do I know GS power is given by 2 and 1 in each of these terms? Well, what determines the power of GS here? MS, I definitely know, but what determines GS power?
So you have to actually look at the expansion in the string theory of the coupling. So these are from taking the full, this is from taking the full like perturbative expression in 10D and reducing it. So it comes from looking at what order these terms show up in.
Is there some simple rule which determines power GS in this effective Wagner theory? Like if you have a MS cube and then there must be GS squared. If you have single MS, single GS.
Let's see.
There's some simple counting.
There is a volume scaling with GS, I believe, in these theories. But I'm not recalling it off the top of my head.
But isn't it just open string versus closed string, right? You get, because you say the standard model groups come from D branes,
Mm-hmm.
and gravity comes from the bulk. So the bulk is closed string and gravity.
Gauge group is definitely coming from, that's the excited state of open string, but
Yeah.
this graviton is closed string.
Yeah.
So
Yeah, that's the
this
G
is
scale.
language. That's 2 open strings.
Yeah.
I see.
Stuck together.
Yeah, so it's just the scaling there.
I see. So single power for the set state of open string.
Thanks. Okay, great. So in terms of the gut coupling and M Planck, we can rewrite this expression and we get that FA here is equal to alpha gut over the square root of 8 pi squared times M Planck. Now plugging in alpha gut is 1 over 25. This gives us 1.1 times 10 to the 16 GeV, which again gives us a mass in this range at about 10 to the minus 10. So that's what happens if you try to just have a simplified 5D example. Now, if you want to look at the full 10-dimensional theory, then you're compactifying on a 6-dimensional manifold X6. X6, we're going to talk about both the case where X6 is factorizable and where it's not. So if it's factorizable, it's just the product of some XP times X6 minus P. So just to give you some notation, BP here is the Betti number. It's the number of independent P cycles. So P-dimensional submanifolds, basically, that are divisors. And these form a basis of the homology group. And the dual basis to that, I'm going to call, is referred to as omega. Omega is normalized so that when I integrate it over the full manifold, it gives me 1. I'm also going to work here in volumes in string units. So when I integrate 1 over the full manifold, I'm going to get something suppressed by powers of ms. So here, the p-form gauge field, CP, gives axions when integrated over p cycles. And so CP is going to give axions, these A here, where CP is equal to 1 over 2 pi summed over that times omega. Now we're going to restrict in the analytical examples to the case where you have a single axion, but in the numerical examples, there will be multiple. And again, gauge sectors come from p plus 3 branes wrapping p cycles.
From 1 to Betti number.
Yes.
BP, and BP is equal to P6 minus P, right?
Mm-hmm.
Right? PP is
Yes.
6 minus P.
Think.
And that's the whole number. That's the whole number, right?
Yes.
Report.
I think there might be is it H11 or H11 minus 4?
H11 response to B2 equal to B4.
Yeah. There's, yes, I think it's, yes, I think so. So again, we can read off the decay constant from the kinetic term. So we dimensionally reduce this using this relation that just comes from Poincare duality in terms of the 6-dimensional volume and the p-cycle volume. Now we can also read off these relations from the Ricci scalar term and the gauge coupling term. And so that allows us to rewrite FA in terms of square root of x times alpha gut over the square root of 8 pi squared times m Planck. Which reduces to the previous case for x equals 1. Recall x equals 1 is this factorizable case just by definition. So again, since it reduces to the previous case, we end up with something that's within this region. Now this appears independent of volume. We don't have any volume showing up specifically. This alpha gut is fixed by unification. But in order for our calculation to be valid, there are still only certain regions of volumes and couplings where this is valid. So just using this relation here from the previous page that we read off from the gauge couplings, we know that compactified dimension should be greater than or equal to size LS, or our calculation isn't valid, which means that VP is greater than 1. So that gives us a minimum on this G string. And similarly, we want our calculation to be perturbative. So GS is less than or equal to 1. And so that requires VP is less than or equal to alpha gut inverse. Okay, so now let's talk a little bit more about numerical examples. So I've given you a couple of random analytic points that fall within this regime, but it's hard to believe that this is where I generically expect things to appear if I just have a couple specific points. So in the KS Axiverse, we can generate many more theories with multiple axions. So this is technical description of the compactifications we're looking at, but that isn't particularly important for the details of what I want to tell you. We basically use existing procedures from Liam McAllister and his group members and use their package CY tools to perform these computations. So this package allows us to extract geometric data, and then the phenomenological quantities are determined by this geometric data in a known way. So this allows us to do that sampling. So the important quantities, H11 is the number of axions, and in this KS database, there are known compactifications with H11 up to 491. So as before, axions come from compactifying higher dimensional gauge fields. The axions we'll consider are C4 axions, so they come from compactifying a 4-form gauge field. We don't study compactifying other gauge fields, though there are possibilities to do that. Those would just be separate studies. And once you have that, the total volume is given in terms of